See whether it's starting to record. Yes, it's recording. Well, good evening, everybody. Thanks for joining online. I thought we do this online, so actually, Elizabeth, you see some faces of everybody. Also, it is a little bit easier in terms of kind of interacting. So Elizabeth is joining us today, giving a guest lecture on smart contract security assessment. That's going to be about an hour, and then we'll talk about the midterm, do our lecture on blockchain security, and talk a little bit about the upcoming assignment. So that's what's on the agenda today. And Elizabeth, welcome, and take it away.
Okay, so hi everyone. Very happy to be here. Today I'm going to talk about program analysis of smart contracts, and I'll go over a bunch of different techniques to automatically find bugs and ensure correctness of smart contract code. So program analysis is the process of automatically analyzing the behavior of a program regarding some property. So in general, you're checking for some property or specification. And a program specification is something that describes the result that a program is expected to produce. So you can see in this picture, you take an implementation and a specification, and a program analysis algorithm will come back and tell you either, yes, your implementation matches that specification, or no, it's buggy. And there's a number of techniques to do this. So for example, you could just execute the program with various inputs and actually observe if it matches that specification. Or you could analyze the code without running it and kind of reason about all the possible paths and behaviors that the program might take. And these different techniques have various trade-offs that I'll discuss. So first, a very important ingredient to program analysis is the specification, or the property which is expected to hold. This is really important because it's the thing that you're checking against. So a bad specification can only get you so far in terms of analysis. But there's two broad classes of these specifications. The first is a precondition, which is assumed to hold before a function executes. In Solidity, preconditions are usually defined explicitly using these requires clauses. And a postcondition is something that is expected to hold after the function executes. These are typically implemented as assertions. And so the postcondition is only expected to hold if the precondition also holds. I'll show you an example of that. So just quickly, we have a function set data. Our preconditions are that the data is valid and the data was updated. Yeah, Solidity has this really nice syntax on their function signatures where you can specify the preconditions as shown here. And then the postcondition checks that if the precondition holds, the postcondition also holds. Okay. So for example, suppose we wanted to check that some function f was monotonically increasing. This is an assertion, it's a postcondition. And so this function f, first of all, we make sure that there's no integer overflow. And f just multiplies by 42. So the postcondition that we want to check is that it's always monotonically increasing, that f of b is greater than f of a. Of course, if you just put any inputs into f, this won't hold. So we have our precondition as well, that b must be greater than a. And then we could also, here's another example. This code searches for a maximum element, and then the postcondition that holds means that the maximum element has to be greater than or equal to all the elements in the list. So these are just some descriptions of properties or specifications we might want to check against. So there's many classes of these techniques for analyzing programs to check for these specified properties. And these techniques have trade-offs. mainly between the cost of developing that technique or running that technique in terms of setup, how long it takes to run, and ease of use. And the trade-off is with confidence. They have various degrees of confidence in correctness. So for example, if you have a C program which you want to test with 10 different inputs, and we observe that on those 10 inputs, it never has a seg fault or it never crashes. That's super easy to set up and run. It's just actually executing the program and sending it some inputs and observing the behavior. But it doesn't provide any confidence beyond those inputs. So this is our ad hoc testing, very low cost, but you have a lower degree of confidence. So imagine that we wanted to show that that property actually holds for all inputs. This is the other end of our spectrum, our landscape, and this is formal verification. It requires a lot more cost than testing, but it also provides a much higher degree of confidence that your property actually holds on all of the inputs. So in this lecture, I'll go over all of these techniques. I'll start with the lowest cost and lowest confidence, and I'll go all the way to formal verification. So the first I'll talk about is testing and fuzzing. Okay, so I looked through your syllabus, and as an example, I'm going to use the first program from your Etherenaut homework. So I'm not sure if you've already done that, but I'm going to give you the answer here. So the bug is that if you call contribute with a message.value less than or equal to this, and then you call the fallback function, you'll be able to pass the requires because you've contributed, you'll become the owner, and then you can withdraw. So the sequence of calls to trigger that bug is contribute with the value less than this, fallback, and then withdraw. So if you're testing this fallback function or fallback contract, say you're the developer of this contract, you might write some unit tests like you see on the right. And so usually when you write a unit test, you check the behavior on a small set of specific values. So say in the first test, we're going to check the happy case where you're sending a value which passes the precondition. And we want to say that if you contribute that value, then the contributions mapping actually updates accordingly. And then maybe you also might try testing with some smaller or larger value, which fails the precondition and expect that it'll revert. And then maybe you'll check that only the owner can withdraw. So yeah, with this kind of testing, developers usually only check natural cases or things they were expecting when they wrote the code, and they wouldn't have checked this pathological path where you call the fallback and become the owner. Right, and this only is checked on a small subset of specific values. But in this case, values weren't the issue really. It was that we didn't expect this sequence of malicious calls. So in general, devs will often miss these unnatural corner cases. So testing is easy. That's why it's done in practice in industry. It's very common and widely used. So it's easy to write and set up. But ideally, we'd want our test to use various values for message.sender, message.value, and different arguments. And so unfortunately, when developers write tests, they usually only test a small subset of specific values. And even worse, they only test sequences of calls which they expect. So enter our next technique, which is fuzzing. Fuzzing or fuzz testing is an automated technique which involves providing unexpected or random data as inputs to a program and then monitoring for any property violations. So it's inspired by this infinite monkey theorem, which is that a monkey hitting keys on a keyboard will eventually write complete works of Shakespeare. And so this is the inspiration behind fuzzing, which is that if you just throw random inputs at a program for long enough, you're eventually going to find one that crashes, or find like a hack in the case of smart contracts. So the first fuzzing study was done in the 1990s. It was actually a final project for a course. And so the first ones were only focused on command line programs. They just bombarded a bunch of Unix programs with random data very, very quickly. And so this has expanded as time went on to inputs with structured data and even GUI-based programs as well. So in that original 1990 study, they tested almost 100 Unix utility programs, and more than a quarter of them, almost a third, yeah, like just they found bugs in so many of these programs. And so these bugs were also reported to the developers of those programs. And so many of them were still present. So the lesson learned, yes.
I don't know what you see on your screen, but Oleg has his hand up. There's a question.
Oh, okay, yeah. I don't.
Hi, Elizabeth. Can you hear me?
Yes.
Okay. Just have a question about the fuzzers. So are these inputs actual programs? Because the example you just gave was source code, right? So is the fuzzer, in the sense that you're talking about, it generating random code, or is it generating perhaps semantically correct code that has random semantics, I guess? Like, at least it uses the name of a function, right, instead of random garbage letters, right?
Right. So apologies, it's not generating a program, it's generating inputs to a program.
Okay, thank you.
Yeah, so like in the example that I showed way back here, we're not generating what's on the left in fuzzing. I'll show a better example, but we're generating things like this value, or who the sender is, or that we're even calling contribute, since there's a number of functions we could call. But yeah, so just in general, the idea of fuzzing is that let's just bombard the program with inputs and hope that we hit one that's bad. Okay, right. So when they did this study, they crashed so many Unix programs, but after they reported them, many were still present. The developers never fixed them. And the reason for that was because, first of all, they didn't have any security implications. And so this implied that many of the bugs that we find in fuzzing are so unnatural and so different from what humans actually do that the developers said, like, we don't even care. But this is a really exciting time for smart contracts because correctness is extremely important. So a few years later in 1995, they found that the getS function in C didn't include a parameter which limited the length of the input to be read. It's a pretty famous bug. And so then the programmer made this assumption, and the tests that they wrote also included this assumption, and they only found it with fuzzing. And this was one thing that was actually fixed, one of those bugs that was actually fixed by the developers. And so the lesson here is that developers write tests which match what their intended use of the program is. And so fuzzing can give us those corner cases that the developer didn't expect, that, oh, hey, someone might give this wacky input. So since that 1990 original study, there have been 3 generations of fuzzers. And they've gotten better each time. So in the first generation, this one's the simplest. Inputs are generated entirely randomly. They're just fed to the program, and then you monitor it to see if it crashes or violates some property. But so performance here was pretty poor. Performance meaning the time between starting the fuzzer and finding a bug. And this is because the inputs are entirely random. And so there's no guarantee that they conform to the expected input of a program. So in like a really complicated case, if you're fuzzing a image parser, most of the inputs you give aren't going to be in the format of an image. They're just going to be nonsense. And then even if we somehow come up with an input which does conform to the specifications, it's not guaranteed to take an interesting path through the program. The same path can be taken millions of times by millions of different unique inputs. And so this first generation had very poor code coverage, especially in programs with a large amount of paths or many possible different executions. So then in order to combat that performance issue, the second generation of fuzzers was produced. And this was for the case like an image parser. And the main insight here is that with a set of seed inputs given by the developer, now the fuzzer starts with inputs which are normal, which are expected, and which conform to the expected inputs. And so now most of these inputs aren't completely thrown away like they were completely randomly. And instead, we can pick that input, send it through the program, and then for the next iterations, mutate it. So instead of coming in entirely randomly and hoping one conforms to the expected input, we start with ones that are expected and make small changes to it. And so this one had much better performance, but this generation was still not sufficient in terms of code coverage. So this third generation really tried to combat this code coverage issue. And the way they do this is with a feedback loop. So like the previous generation, they start with a set of seed inputs, and those are randomly mutated to try to trigger the bug. But then they have this feedback algorithm where each input is run and monitored, and then you tell the fuzzer if it's interesting or not. Usually this interestingness is based on code coverage. So you run on an input and you'll check if the code coverage increased. And then if so, you'll keep that input and mutate it further. If not, you'll just throw it away. And so this third generation increased performance of fuzzers a lot. It made fuzzers really, really usable and tested like really difficult paths to reach in your code. So there's like two very popular fuzzers. The first is AFL and libfuzzer, and both of them use this coverage feedback. And so although this is the third generation of fuzzers, fuzzing isn't like totally solved. There's still a lot of these issues. And in terms of things like the developer getting seed inputs and right, so there's still much research to be done on making this entirely automated. But it's made huge performance increases since the first generation. So what kind of bugs can fuzzing find? For C programs, it's very clear what the specification should be for these types of cases. Like there should never be a seg fault. There should never be a memory error in C. And so the developer doesn't need to tell the fuzzer that these are the specifications. Other than assertion violations, they'll have to write those. But there's these kind of safety errors in C that should never happen regardless of what functionality you've implemented. But smart contracts are very unique and they're tough to analyze because they don't have these safety properties, right? There's no seg fault, there's no crash. So instead, our program analysis will check for assertion violations would need to be written. And there's also panics for things like array out of bounds. But in general, this is a unique problem to smart contracts, that there's no clear definition of a safety violation. Okay, so the fuzzers I just talked about were kind of the AFL class of fuzzers, meaning they just send random inputs to the program and they're not concerned with creating a trace. And so there's this other class of fuzzers that their goal is to generate tests, kind of like more natural sequences akin to unit tests that a developer might write. So the most famous one is for Java. It's called randup. And you can see it sets up a bunch of different objects and then calls some methods on that object and then observes the behavior that there is an illegal argument exception. So the way this works is that randup makes sequences of calls. That's the important thing to note here. So for fuzzing smart contracts, there's these two major fuzzers, Echidna and Foundry. Echidna is similar to randup, and Foundry is more similar to AFL. So Echidna is a smart contract fuzzer, and it makes sequences of transactions, similar to how randup does. And it's basically creating like a blockchain sequence of transactions. So if you look at Etherscan, you'll see like here was the call, this was the value, and this was the sender. And that's kind of what Echidna is trying to mimic. So I ran it on the level 1 for Etherenaut, and you can see that it found that if I call contribute with some value, the fallback function with some value, and then withdraw, there was an assertion failure. I did have to write this assertion because there's no clear safety violations in smart contracts, but it did find it, and it found it fairly quickly. And Echidna is also coverage guided in the following sense. It'll call contribute, and then it'll add something else to this sequence. So let's say it calls contribute twice. It'll see that, you know, coverage didn't increase, so it'll cut that second call and then try to add a new call, which does increase coverage. Yeah, and so I think Mark has a question.
Yeah, so I just a quick clarification on on coverage. Is it trying to see like what it can reach within this like the smart contract or function, or is it like what do you mean by coverage in that sense, I guess?
Yeah, so it's the lines which are executed in the smart contract other test.
Okay. And you just wanted to like if you want to find a bug that's able to reach like throughout the whole program, then that's bad, or you're talking about just through like I guess how do you specify in terms of like how much something can reach in terms of like if that's good or bad, I guess. I don't know if I asked that very well.
Okay, so I think coverage is always good because if there's a bug somewhere in your program and we execute all the lines in the program, we're probably going to hit it. But like fuzzing would be bad if it only kept executing the same lines over and over again.
Okay.
One of the nice things with fuzzing is that it also indirectly ends up testing like libraries or other things that you've taken dependencies on potentially, because it's throwing this random set of stuff at it, and it will eventually surface like an underlying issue that you may not have anticipated. So, you know, this is nice because it's a like a one level depth, you know, into it, but you can also start to test through multiple layers potentially and find unexpected interactions or, you know, memory issues or other things.
Yeah, that's a great point. Especially with smart contracts, you sometimes will need to interact with external contracts that are already deployed on the blockchain. And a lot of times developers will make assumptions on what that contract will output. And so fuzzing will find when those assumptions are violated.
Cool. Thank you.
Yeah. Right, and so then there's our second fuzzer, Foundry, which is more similar to AFL. And so for that, you know, it looks like a unit test, but instead it's parameterized, meaning that instead of testing that if I transfer 1 ether and I withdraw, then the amount should increase by 1, it randomly sends numbers for this amount. So this addresses one of our issues with ad hoc testing, is that now we get random values. However, it doesn't address our second issue, which is that we should also get randomized sequence of calls. So like in the Etherenaut example, our issue wasn't really that we were not testing with a large set of values. It was that we didn't anticipate this pathological call to the fallback function. So Foundry doesn't really address that, but Echidna does. But it's a trade-off, because the good thing about Foundry is that you're telling it how you expect the user to interact with this program. So it shrinks the search space a lot. But it's a trade-off, because if you shrink the search space a lot, now you're not testing outside of what you expect. But they're just two different paradigms of fuzzing. So in general, randomized testing and fuzzing is highly effective, and it has a number of trade-offs. The first is that it's easy to implement, it's easy to use, it typically has good coverage so long as you run it long enough, and it's really appealing in security. Cons is that you might get an inefficient test suite, meaning that you might send 1 million unique values, but they all take the same path. So you're kind of wasting cycles there. It might find bugs that don't really matter, like in the Unix study, where most of them weren't even fixed. In smart contracts, it might be a little bit more, because we really care about correctness. But even then, sometimes you find bugs that are unexploitable and they don't even get fixed. And then this is also a con and a pro, but you might have poor code coverage. There might be some branch that you just never reached, just because of the nature of fuzzing. Does anyone have any questions on fuzzing before I get to the next technique?
Yeah, would you say that it's like a valid concern that even if you discover a bug that isn't exploitable on a given day that you discover it, it could become exploitable later as smart contracts are composable, and you could introduce, later on, the vulnerability could be introduced?
Yeah, definitely. And that's why correctness is so important here.
How is costs kind of managed for these? Because, like, you know, I think about fuzzing costs in a traditional environment, and it's basically just my compute cost of my test environment. Mm-hmm. When I switch over to doing this on, you know, on the chain, there's the risk that I'm, you know, burning transaction fees and kind of like, you know, I guess it's still, I mean, it's power of a computer somewhere, so it's maybe equivalent. But are there good practices to kind of prevent like a runaway, you know, fuzzing session? I mean, I guess you just associate it to a wallet that has what you're willing to spend, I guess, is maybe one way to do it.
Yeah, so mostly people will test these on like local blockchains, but then you get into issues that, right, so you test on local blockchains, you don't have to spend test gas fees or whatever. But then you run into the issue that, okay, I'm interacting with some external contract which is deployed on mainnet. So how do I test it? Okay, well, I could download that source code and deploy it at that address on my test blockchain, but now it's in its original state and not the state that was actually on the blockchain. So now I need to execute the calls that got it to that state to set it to the correct state. And then what if on mainnet that contract changes and now I'm still interacting with it? Yeah, so in general, it's really difficult to test against the blockchain state, which might be changing, but usually the answer is just test on a local blockchain. Okay, cool. So symbolic execution is the next I'll talk about. It's more expensive in terms of cost than fuzzing, but has a higher degree of confidence. So here's an example of a reason where fuzzing can go bad. If you have some test me function and it takes an input x, only if y is equal to 13 will you hit the error. So you can test, right, your chances of getting an x equal to 10 is very slim. However, random testing is black box, so we don't even know that this constant is here. We don't know that this branch says y equals 13. We're just sending random inputs. And so for real world program, the space of inputs is just massive, and the chances that we'll reach this branch condition are pretty low. So what symbolic, right, okay. And so like if you're testing a compiler, this could get really bad. Most of the time when you're fuzzing, you won't even get past the lexer, and then the odds of you getting further downstream are just so small. So this shows how black box fuzzing can go bad. So the idea behind symbolic execution is that we only want to test each path once. In fuzzing, you can generate millions of inputs which go down the same path, and it's a waste of iterations. So the idea in symbolic execution is to represent these branch conditions as constraints and then solve them for the input and only explore that branch one time. So here we might say, let's test when x is equal to 10, and then test when the if fails, some other input, say 100. So you can visualize how the program will look based on the different branches. These numbers are just depth first ordering, which is how symbolic execution usually explores programs. But so each node is a condition, and then each edge represents if you're taking that branch or not. And in general, this tree can get very large. So here's an example of the computation tree. Each node is a equation for the branch, and then you can take the true or false branches. One last point is that if you have loops, this tree can actually become infinite. And usually what the developers will do is they'll make some trick like, okay, let's just say that you can only execute this loop 3 times maximum. Because usually executing the loop 3 times versus 100, you'll probably get the same behavior. But that's another source of error because it's a heuristic. Okay, now symbolic execution is cool, but let's see what else can go wrong. So suppose we have a contract test and we make a call to an external contract, price oracle. So if Oracle has branches in it, how do we make sure we're also exploring all of those paths? Well, one solution is that we could actually take the code of Oracle, inline it right here, and analyze those branches in a white box manner. But this can get out of hand pretty quickly because what if Oracle also refers to another external contract? So there's a technique called dynamic symbolic execution, which kind of exploits the beauty of fuzzing, which is that we don't care what the code looks like. We just want to observe the execution. So what dynamic symbolic execution does is when it gets to a point where it gets stuck, where if we're looking at this white box, it just gets out of hand, it just runs it and it looks at the concrete value and it plugs that into the formula. So this is kind of like dynamic symbolic execution is kind of like a combination of symbolic execution with fuzzing. Okay, so then symbolic execution of smart contracts. There's 2 main symbolic execution engines, Mithril and Manticore. I ran Mithril on that first level of Etherenaut, and it did find the output, contribute with some value, fall back, and then withdraw, and it even has the message.senders. So when I ran it with fuzzing, it found it in like under a minute. Can anyone guess how long it might take for symbolic execution to find that same bug?
1 second.
1 second? No. It has to explore all of the branches in that program. I could go back to it, but it was far. Right, okay. So think about all the possible paths that could be taken in this program. It's not a very big program, but it still has a lot of paths. Any other guesses?
10 minutes.
Closer, but still way too fast. This took 2 hours and 15 minutes, even for this toy contract. So symbolic execution is really cool. You get this degree of confidence that it's actually executing all of the paths in the program, and each of them only once. But even for tiny programs, this just becomes so unmanageable. I talked to some folks who implemented a symbolic executor for smart contracts, and they told me that any transaction sequence of longer than 3 calls becomes so unmanageable in real world contracts, it would take months to find it. Yeah, go ahead. Okay, yeah, so pros and cons of symbolic execution: higher degree of confidence, 100% branch coverage. It explores every single path. So if a bug exists, symbolic execution should definitely find it, but it's super slow because of the constraint solving. So here to find what X should be, I mean, this is pretty simple because there's only 1 branch, but once you have 10 different branches, this formula gets huge. And then finding an input which satisfies that is what makes it really, really slow. And because we have to do it for so many different conditions, that's what makes it take so long. Okay, our next one, static analysis. So we're moving more towards the higher degree of confidence, but higher cost. And you'll start to see that as we move towards higher cost and higher confidence, these techniques are rarely used in industry software, only where a high degree of confidence is absolutely necessary. So static analysis is a different paradigm. It refers to reasoning about the program behavior without actually executing it. So a linter is an example of static analysis. It just quickly checks your source code and it tells you if there's some error. So a robust static analysis will actually model the effect that every statement has on the state of the program. So Slither is a static analyzer for smart contracts. It's pretty popular. And it runs a suite of vulnerability detectors and prints some information if any of these are violated. So this is a list of just 11 of them, but there are 88 total. And so there's things like you shouldn't have multiple constructors, or you shouldn't have this suicidal behavior so anyone can arbitrarily destroy your contract. So here's an example of one pattern they check against, which is that you shouldn't use transaction.origin to validate the owner. And what they do is they represent the program as a graph, and they look at all the nodes in that graph, check all the if statements or requires, and they see if any of them are transaction.origin. So they never execute. This one's a very simple static analysis. It's like a linter. It just checks if some pattern is matched. So to show the power and confidence in static analysis, there's another trade-off I'll talk about. They're called soundness on the y-axis and completeness on the x. So soundness implies that if a bug exists, the analysis will report it. Completeness, on the other hand, implies that the analysis will report all of the bugs. So fuzzing is unsound, but yes, unsound but complete. Fuzzing is unsound but complete. Every error it gives you can truly be reached because it even gives you the input on how to reach it. So there's no false alarms, there are only true alarms, but it might not report all of the errors because it might not ever give you an input which reaches them. So static analysis is sound but incomplete. It reports all of the errors. If a bug exists, it'll tell you about it, but it also might report some false alarms, bugs that don't actually exist. One interesting thing is that there's no analysis algorithm that can be both sound and complete. This, if you're interested, this is provable that we can never have an analysis that's sound and complete. It boils down to the halting problem. I can send some resources later, but the idea is that this is never going to happen, so we have to sacrifice either soundness or completeness. And I'll show how static analysis has false positives. So in a really simple example, if we're checking for divide by zeros, let's say we have a switch on an enum value that only has A and B. So we know that X will be equal to 1 or 5. Depending on the precision of our static analysis, they might not actually check that there's no default case here. So the analysis might think that X could still be 0, and it might report a divide by 0 here. Like if we were doing fuzzing or actually executing the code, it would never report that to us because there's no input value which would give us 0. Okay, so now let's look at a more complex analysis. This is a graph version of our program. We want to ask, will this ever crash? So I'll give you a few seconds to look at it. Any thoughts on if this can ever crash?
Did Y ever get initialized?
Let's say that Y was initialized somewhere up here with some value we don't know. Let's say Y came from an external call.
Then the crash path is theoretically not reachable. Because in the condition that Y is 0, you go no, exit. And X decrements on that path. Otherwise, X is set to 0 and X goes up. Well, there's an unhandled crash scenario for sure. Like that is, I guess, possible, but X will never get to 0.
Correct. So if Y is equal to 0, that's the only way that we can hit this path condition. But the only time that X is less than 0 is if we take the no branch. So no matter what input we have for Y, we should never be able to get this crash. Yeah, pretty difficult to reason about statically, especially because of this loop. So if we're going through and we're thinking about what concrete values would happen, okay, X is 0 here, 0 here, 1, 1, we take the yes branch, now we take the no branch, and we're back in the loop. So using concrete values for analysis algorithm might lead to some non-termination. So usually the way they solve this is using abstraction. So instead of tracking the actual values of X, instead, hey, let's just track if X is 0, positive, negative, or T, meaning we don't know, it could be either. So as we go through this analysis, we'll say that X is 0 here. If Y is 0, cool, X is still 0. Then we increment by 1, now X is positive. But if we take the no branch, X is negative. So when we reach this branch condition, X can either be positive or negative. And so here we just totally lose precision, and our static analysis will not know if X is negative at this point, it'll report this crash as a false alarm. So this is how we get false positives. So static analysis, it's sound, meaning that if a bug exists, we'll report it. But because of that, we also have this trade-off where we can get false positives. It's also pretty fast. When I ran it on the Etherenaut levels, under a second, because it's just doing these checks on the AST. So the cons are the false positives. It has quite a bit that you have to sift through, and as a developer, that can be really annoying if you're running a tool and every time it gives you 10 errors and none of them are something you actually fix. And again, it requires these predefined universal checkers. So if you want to check for something like program specific, that might not be very simple. But if you want to check for something like you should never validate with transaction.origin, those things can be predefined up front, and Slither can implement those as one of their AEs checkers. Any questions on static analysis before I get to the last one? Cool. So formal verification. This is our highest degree of confidence, but also highest cost. So formal verification is the process of actually proving or disproving the correctness with respect to that specification. So formal verification actually historically has made its way into industry in very few cases, in things like airplanes, cars, medical devices, but your average software engineering probably won't be formally verified. But in smart contracts, this field is like really exploding. Developers and firms are really concerned with actually ensuring that their smart contracts are correct, and they're willing to put in that cost to do so. So there's a lot of different companies that are doing formal verification of smart contracts. One of them, big one, is Certora. They have CVL, which is the Certora verification language. And actually SolC, your compiler, comes with a verification engine out of the box. So if you add assertions and you run with some flags, I can send some resources about that as well. It'll do it right out of the box for you, which is really cool, and I think shows how important correctness is in this domain. All right, so back to this monotonic example. Let's say we want to formally verify that f of b is greater than f of a. There's this formal verification engine, this SAT solver called Z3, which was developed at Microsoft, I think decades ago. And basically what you do in formal verification is you encode the specification in a logical formula. And Z3 will come back and say either yes, that formula is satisfiable, or no, it'll never happen. So we encode the error condition. So we want to show that f of b is greater than f of a. We check that the case where f of b is not greater than f of a. And if this formula can ever be satisfied, then we know there's a bug. So I ran this in Z3 and it came back and said it is satisfiable. In the case where a is greater than b, a is 2 and b is 1, of course, this property won't hold. So you can go ahead and add this precondition that when b is greater than a, this should hold. And then Z3 will come back and say unsatisfiable, and we've proven that this property holds for all inputs. So this isn't actually quite true. There could actually be an integer overflow here, but to model in Z3 that x is always greater than 0, not an integer but an unsigned integer, is extremely difficult. And you have to you have to represent x as a bit vector. Like the way that integers are actually represented on your program, that's what you have to feed to Z3. So when I was coming up with this example, I tried to do it, and it was so complex, which just shows the cost involved with verifying real-world smart contracts. So formal verification is sound. If there is a bug, it will report it. It's provably correct, so it has the highest degree of confidence. Cons is that it's slow. Just like symbolic execution, when you're solving these constraints, it takes a very long time. And as the constraints grow, it takes a longer time to get your answer. They're also difficult to write. So if you're not sure what your specifications should be, it's even more difficult to write. And for all of these analysis techniques, your analysis is only as good as the specs you write. Like if you write a bad property and you like prove or show that it always happens and is trivial, of course. But it's like a really big deal for formal verification, because when you're using these tools, you expect a very high degree of confidence. But if you're writing weak specifications, it's kind of a misplaced trust. So usually formal verification is in the hands of like highly trained experts in very correctness domains where you really, really need correctness. I think Oleg has his hand up.
Yeah, can you comment on like the practical distinction between making sure your code is correct to begin with and writing the specs correctly so that you formally verify your code, because you can make an error there anyway. So what is the distinction between writing correct code and writing correct verification of code?
Yeah, so usually it's good to separate who writes the specification and who writes the implementation. Because if the person who writes the specification also wrote the code, they probably made the same mistake twice. So writing specifications should be logical formulas of the intended behavior of the program. And then actually writing that implementation is the code. I'm not sure if that answers your question. Can you maybe clarify?
Yeah, I think you answered it. It sounds to me kind of like it's a really, really rigorous code review is effectively what's happening here.
Exactly. I think that was all I had. I went through the entire spectrum. If anyone has any questions on formal verification or any of the other techniques.
Sorry, I just might have missed it, but what's your what's your field of research in, I guess? I think I joined a little late to the meeting.
Yeah, I work in program analysis. My thesis is using machine learning to infer these specifications. So usually have to write them by hand. Usually have like a domain specific expert that comes through and says like, hey, seg fault should never happen in C, or like more complicated things. So my research is on inferring those, and in general inferring functional correctness. So like a seg fault should never happen is a safety property, meaning it's true for all programs. But if you're writing specific assertions for correctness on how your program should behave, you have to write those manually.
Okay. Cool. Sorry, just wondering.
Yeah.
Well, Elizabeth, this was an excellent presentation. Thank you so much for coming on, especially given how late it is. I personally learned a lot, and I'm sure the class did too. So thank you very much.
Thank you for having me. All right, bye.
Thank you. Bye.
Thanks.
All right. I hope you all enjoyed that. That was excellent. All right. What I want to do